Welcome friends, I am Conroy. So today we will discuss about the stability of carbanion. So before going to the details, let me first discuss what is carbanion. Carbanion means, so if we check the outermost valence electronic shell configuration of carbon, that is 2s2 and 2p2. So and it undergoes sp3 hybridization. Okay, so what happens? C sp3, 4 sp3 hybridized orbital having single electron, and it forms bond with different substituents. For example, if R1, R2, R3, if we consider, this is with R1, this is with R2, and this is with R3, and this is a carbanion, means another meaning. This is the carbanion. So this indicates that one unit negative charge is given on carbon. Okay, electron is given on carbon. That's why it became carbanion. If we compare with carbocation is a 6 electron species and electron deficient species, means electron is withdrawn from carbon, but here electron is given to the carbon. So this material is octet filled. Okay, it is not octet unfilled, it is octet filled. Electron density, and majority of cases its hybridization is sp3 and its structure is pyramidal. Pyramidal means this carbon attached to 3 substituents, R1, R2 and R3. And in case of, since we don't consider the lone pair which contains a negative charge, for this geometry, actually this looks like pyramidal. Pyramidal means this, this and this. So it's pyramidal. Okay. So this looks like pyramidal, and here if we consider, this is a lone pair LP and this is a bond pair BP. From VACPR theory, means valence shell electron pair repulsion theory. In short, VACPR theory, lone pair bond pair repulsion is more than this BP bond pair. So LP BP repulsion is greater than BP. Okay, this is the basic, and actually these are reactive intermediate. These carbanions are reactive intermediates during the reaction. It is produced during the reaction. And third point, they are nucleophilic in nature. And more specifically, if we say carbon nucleophile, they are carbon nucleophile. So this is the basic introduction about this carbanion. So after that, we will discuss little bit about the synthesis of carbanion. How carbanion could be synthesized? Carbanion, as if you see my butyl lithium, I suggest you to read that butyl lithium talk. So you can see that butyl lithium is prepared by reacting this alkyl halide, for example, RX with lithium. It produces R11. And R is minus, Li is plus. Similarly, if it reacts with metallic magnesium, it produces RMgX. So general strategy is that a metal which can donate its electron easily, what happens? It donates its electron and became Mn plus N electron, and this electron is given on this bond to generate carbanion. So in the initial I told that carbanion means 1 unit of extra electron is given to the carbon center, and this example indicates, okay, actually their synthesis is following that track, means to generate carbanion you have to give electron density to the carbon center. Okay, so right now we will discuss about the main point, that is stability of carbanion. Okay, so what factors are responsible for the stability of carbanion? For carbanion stability, factor responsible one is -I, minus R and minus H. Actually, I will suggest you don't say always that minus H, because this is nothing but hyperconjugation. Means absence of hyperconjugation. I will explain this factor. Okay? And this is resonance, this is inductive effect. So before going to the each point, let's learn about the basic concept. Basic concept means it's a carbanion, electron rich species, and we know that carbon is not that much high electronegative atom. So what happens? What happens? This carbon has a very high electron density. What is the real example? Real example, if you see this butyl lithium, tertiary butyl or N-butyl lithium, they are very much reactive. They are very much reactive, means negative charge on carbon is not that much stable. Why? Because it's not that much electron rich to keep the charge on itself. So how it could be stabilized? Means its charge should be delocalized or taken or dragged to somewhere else. So it needs electron withdrawing group, EWG. So attachment of electron withdrawing group will stabilize the carbanion. So this is the basic concept. Keep this thing in mind, I will explain. So let's discuss about our first example. First example means methyl minus this ethyl minus this isopropyl minus, and the last one is this tertiary butyl minus. What is the stability order of this carbon? If we check the stability order, I'll give you first the answer, then this. This is sorry, I made a mistake. This methyl is more stable than this ethyl, than this and this. So tertiary is the maximum unstable. This is actually the reverse of carbocation stability. Carbon, this is first, this is second, this is third, this is fourth. Means reverse of carbocation stability. Question is why? Okay, before explaining the actual answer, I will give you a real proof. Real proof means if you check the stability of this tertiary butyl lithium versus N-butyl lithium. Tertiary butyl lithium is strong base, very strong base compared to this. It's very reactive, means it's a pyrophoric, means in atmosphere it catches fire, but it doesn't catch fire. It's not that much pyrophoric or that much reactive like this tertiary butyl lithium. Okay, so this is one of the real proof. But this explanation is saying actually it's right. Second, why this is happening? Generally, it is said, but said that methyl group has plus I effect. That's why it pushes electron density to this carbon center. Second point, this carbon center is already more electron rich. So if additional electron is given, so carbon center became more unstable. And this is the reason, this order. Actually, you can say here instability increases due to the conjugation, and here instability is minimum. Okay, instability is minimum in case of this methyl group. That's why it is relatively more stable among this. I will give one of my another opinion later on at the last phase of this video. So next example we will discuss about the effect of hybridization. Effect of hybridization on the stability of carbon anion. Means sp3, sp2 and sp. But sp3 means, for example, this R1, for example, if we take simplest example. Okay, so if we consider this sp3, that is methyl minus, sp2, that is this ethylene minus, and this is acidity. Let's give one substituent in case of this, then less confusion. Okay? Okay. So what is the stability order? Actually, the stability order is this. This alkyl is more stable than this. Why? Because of the hybridization. Hybridization means, if we consider sp3 withdraws or drags electron density more towards itself. That's why it stabilizes the carbon. So before going to I'll give you details how sp3 is formed. This is a s orbital and this is a p orbital. This is a p orbital. Okay. So when it mixes, it produces a sp3 orbital. Looks like this. Okay. This is the center of nucleus and this is the 3D space where the probability of finding electron is maximum. So this is sp3. Now, if sp2 form means one s orbital, two p orbital. Here one s, three p orbital. Then p orbital contribution will be less. So it will looks like this. So this is sp2. And if 1s 1p combination happens, then what will happen? It will remain one unit further close, means this is the sp. It's a qualitative idea. I want to give you a rough idea. Means what does it mean? That electron goes far apart from the nucleus if the orbital is sp3. And if it is sp2, it's moderate distance, and if it is sp, it remains closest to the nucleus. And we know electron is a negative charge species. It stabilizes when it remains closer to the nucleus. So that's why this is relatively more stable compared to other two. So now you can understand how this happens. And another real example of this, for example, this alkyl with explanation is butyl lithium. This can react with this halide substituted to produce this, or it can react even this, or even it can abstract the proton also to give this. Okay, so it will be more convenient example, proton to this. And third is that it can abstract proton, this alkyl lithium, from this terminal alkyl. This alkyl lithium can abstract the proton from this, as well as this alkynyl, or you can say vinyl. This vinyl can also capable to abstract this proton to produce this anion. So this indicates, this is a real proof of this logic that this sp3 is more reactive than this sp2, and sp is the least reactive due to the stabilization coming from hyperconjugation. Stabilization coming from hybridization. So right now we will discuss about the minus I effect. Okay, minus I operates through sigma bond. How? If you check the bond formed between C and X, this X is more electronegative than carbon, and what the sigma bond will look like? This, and the electron will be in between this. Electron will be in this region. Okay. So electron will be in this region. So due to the more electronegativity of nature, this will attract the electron density towards itself more. So consequently, what will happen? This electron density will go this side. If we consider this for carbon, minus. So it has more electron density. This electron is not dragged directly towards X, but carbon's own electron or this bond pair is dragged toward this X. So in this way, somewhat reduction of electron density is possible, and actually this happens, which stabilizes the carbon. Okay. So let's give an example about it. What example? Okay, before going to the example, let's discuss about another concept about this carbanion. What is reaction is happening? If we consider this, it producing a minus and H plus. It's a different way. Actually, this carbanion is not generated in this way. I have explained, but it's a different concept to understand the next story properly. You can consider this alkane is the acid of this carbanion as well as proton. So what happens? This carbanion and proton generates if the stability of carbanion increases, then it's an equilibrium, it will go this side. So how to increase the stability? For example, if anything withdraws the electron density. A real proof, if we consider methane, this methyl minus is generated from this methane, and this CF3, let's discuss, CF3 is generated from fluroform. Okay. If we consider the pK of this fluoroform, this is around 25 to 28. This is pK, means the acidity. If you compare this, around pK around 50. Okay. So this means this is more acidic. Based on this concept, this is more acidic. Why? Because the fluorine withdraws electron density through the sigma bond, and that's why this bond is more polar, means hydrogen is more plus, this is more minus. That's why it is easier to generate this CF3 minus. Okay. And another thing, fluorine is the most electronegative atom in the periodic table. Second, often it is explained that often a confusion is generated, minus I with minus I. Resonance is the most strongest effect, but often this confusion generates, and this example will clarify that confusion. For example, if we consider chloroform, CCl3, so it generates this Cl minus, and fluorine is more electronegative than chlorine. So it is expected that this polarity will be less, and pKa values from compared to this, it will be less pK. Then this means if it is very weakly acidic, it is moderate, so it will be lesser than this. So pKa is expected to be higher than 28, but actually its pKa is 16. Why? Means here it is more stable as compared to that, although it is a 3p element. So 2p, 3p, 1 point. And another thing, it's less electronegative, but this is because another factor is there. Previously I told that carbanion is an sp3 hybridized. It is true, but when there is a possibility that it can undergo resonance, it changes its hybridization to gain that resonance stability. And that's why it is a sp3 hybridized molecule. So when it is generated, it is also a sp3 carbanion, but after that it rearranges itself to form a sp2 hybridized carbanion. Why? Because then it can undergo resonance. Okay, this is with the vacant d orbital of this chlorine. So in this way it delocalizes electron density and becomes stabilized. So this is, but here that is not possible. Another thing, fluorine, if you consider, it has 3 lone pair. So actually it should be like this. It has 3 lone pair, and it also repels. I have told in previously that according to B.Sc pair theory, this lone pair repulsion is stronger than lone pair bond pair. Actually, it is not directly resembles to that, because bond pair is this, and lone pair means lone pair on a same atom, but not. These lone pair versus this repels each other and results in the unstabilization of this carbanion. Okay. So that's why this speed pK is higher than this. I guess this concept became clear to you. So formally this is the end of this video, but as I told earlier that I will give you an explanation about the stability of this methyl to tertiary butyl carbanions. I will explain what is that. For example, if we consider this methyl minus this isopropyl, I am skipping little, and versus this tertiary butyl minus. So I repeat the explanation again. This is more stable than this because plus I effect of methyl group means this carbon pushes this electron density to the methyl group pushes electron density to the carbon center. That's why electron density increases on the carbon center and it became relatively more unstable. But what is the concept of this plus I? Plus I's concept is electron negativity difference. That's why it pushing happens. If we consider a neutral carbon versus a carbon anion, who has more electronegativity means the tendency to withdraw electron density from the bond pair. Okay. So carbon, at the beginning of this video I told it's not that much electronegative atom, so it don't like to keep the electron density on this center. That's why it become unstable. So it don't want to keep electron density on itself, and forcefully we added electron on it. Then at this condition, will it drag electron density towards itself? It is true. It is not that much expected. So plus I effect of methyl group from a attached to neutral carbon is more compared to this. Actually, it will not try to attract. Otherwise, it will try to delocalize this electron density by pushing. So this is not possible. And here, if you see, this carbon is attached to carbon, means same atom. Here different atoms. So chances to polarize the CH bond is more here. That's why it relatively reduces the electron density by pushing, polarizing, and not possible here. That's why this is less stable compared to this. So think about this explanation. It may be helpful for you. Let me give you another example just some time before I have explained. This Cl, this is trichlorocarbon. It removes one Cl minus to generate CCl2, same as carbene used in Reimer-Tiemann reaction. I will explain in another video this. It is electron rich, that's why it pushes this bond to go out. That's why this, although it is a 6 electron species, this, sorry, it should not be a negative. 6 electron species, this, still it forms. So this is the proof of this thing, and this is the end of the video. So thank you all for listening my this video. I request you to subscribe my channel Chemistry, the Mystery of Molecules, and share this video with your friends, and please press the bell icon such that you can get notification of every single video I upload. Thank you.